We're now going to use our Biot-Savart law to find the magnetic field intensity H at some arbitrary point P due to a straight and finite current carrying filament. So we're going to be using the first of those three integral equations we had in the previous video. So let's take a look at what we're considering sort of graphically. So I've got some current carrying filament, which is finite and straight as advertised. And so this is our blue line here. And so we notice I've sort of arbitrarily said, let's let this line be going along our z-axis. I also have a couple other things labeled on the line. So I've labeled this endpoint at the top as B, this endpoint at the bottom as A, and as we can see, we have this current going from endpoint A towards endpoint B. Now you might be asking yourself, how can we have current if this is just some line segment? Let's not worry about that too much at the moment, but simplistically, let's say, at the top, maybe we have some portion of our wire going into the page. At the bottom, we have some portion coming out, such that we, of course, obviously do have some closed circuit that's allowing for current to flow. But simplistically, right now, let's just look at this simple segment. And over here on the right, we have our arbitrary observation point P. So let's go ahead and define a few more things to sort of set up this problem so we can fit it to our integrand from our previous equation. Well, actually, let's even go ahead and write our integrand from the previous equation. So what we had when considering the Biot-Savart law for a filament current or a line current, we said that the differential magnetic field intensity dH was equal to I dl cross R divided by 4 pi r cubed. So remember, we had the slightly different form that used our unit vector, so either one is of course going to give us the same answer. And in this case, we're asking ourselves, what is this dl, what is our r, and what is the magnitude of that r? So if we figure out these three things, we can then set up our integral. We're going to play some games to be able to integrate that easily, and then we'll have a general expression for h. So, first of all, let's come back to our filament and define some differential length just like we did previously. So let's define some differential length along here, dl, and so that's going to be pointing upwards. So this is going to be our dl in the direction of current. And of course, we can define from that differential length some position vector r, which goes to point P. So this is going to be our position vector. Let's write that a little bit better. So this is going to be our r. And so remember, we're also interested in the angle that makes with our current carrying filament, alpha. And so that direction is going sort of from the line r towards where the current is coming from. So note, I've put it on the sort of downward side of that line as opposed to the upward side here. Okay, so if we want to figure out that distance r, let's add sort of another line here, and let's say we're interested in this perpendicular distance. See if that'll make a straight line for me so it's a little cleaner. All right, let's move that down just a bit. There we go. Okay, and so let's say we have some straight line here such that this is our perpendicular distance. And we can sort of arbitrarily call this distance rho. So that's going to be our perpendicular distance from that current carrying line, the axis of that current carrying line, to our point P. And then we also need to know the distance from that perpendicular location up to our differential length. So since that's along our z-axis, let's call that length z. So now we can talk about that r value. So we can say that let's go ahead and do our dl first because that's the first thing we're looking at here. So our dl in this case is, again, it's going to be upward in that little segment we drew. So that's just going to be the differential length we cover in z in our z direction, so u of z. And we also know now that that r vector is going to be equal to, so our r is going to be equal to rho in the rho direction minus z in the z direction. And so that's just from this triangle that we've made here. And so note, and I'll mention this explicitly or write this explicitly later, that our rho is locally defined. This isn't necessarily the rho that we used for our cylindrical coordinates. One other thing we can point out before we proceed with this problem is, of course, using our right-hand rule, we could determine that our magnetic field intensity at this point P is going to be into the page. So we put our right thumb in line with the current, we curl our fingers, and we see at the point P, they're going into the page. Okay, so we know our DL, we know our R, so now we can go ahead and do our DL cross R. So let's go ahead and set that up like we did back when we were learning about our cross products. So we have DL cross R. Let's make that a little better. So DL cross R, and so if we set that up to do by hand, we know we have U rho, so let's use sort of our pseudo cylindrical coordinates, I'll say here, because again, these are going to be locally defined items, and we'll talk about that a little bit more in a minute. So our DL was 0, 0, and then DZ in the R direction. And for our R, we had rho, 0, and negative Z. So if we go through there and we do that determinant of that 3 by 3 matrix, we see that this cross product is going to give us rho dz in our phi direction. Again, noting that our phi, or our phi direction, is locally defined. So from this r vector, we can also get the magnitude for r, so that's the last of the 3 highlighted items in that equation that we're interested in. So we note that the magnitude of our r vector, which is just r without the arrow, is going to be equal to the square root of rho squared plus z squared. So now all we need to do is plug this information into our integral equation. So we have that our magnetic field intensity H is equal to the integral over the line of, we have our, let's see, coming back up here, our I dl cross r, so we're going to put an I out front of that, and then our dl cross r is the rho dz in our phi direction, and we have 4 pi times that magnitude of r cubed, so that's going to be rho squared plus z squared to the 3 halves. And so what we're going to do to make this a little bit easier is we're going to play some games with trig. So let's see, using trig to make our integration easier. And so this is the same basic process we did when we were looking at a finite line charge and used Coulomb's law. So I'm not going to go through all the details as I did previously, but you can look on page 301. I know the book doesn't often go into sufficient detail, so if you're looking at that and you have questions, let me know and I'm happy to clarify. Before we go through and set that up, I do need to specify a couple other things here as well. So our limits are now going to be based on, of course, the A and B endpoints, but we're going to be doing it in terms of the angle alpha. So let me draw 2 other position vectors. So one that's going to correspond to B, so that's going to look something like this. And so this is going to be some angle which we're going to call alpha sub 2, because that's our ending point. And then we can draw some position vector from A to our point P. And so we don't necessarily need to consider them as vectors. They can just, really we're interested in these angles. And so this angle is going to be alpha 1. And so notice again, I've drawn these angles on the side where the current was coming from. For our alpha 1, that means I'm actually below where the current is. But again, sort of we're not going on the side that the current is going to, but rather the side it's coming from. Okay, so with that information, now we can appropriately set our limits as going from alpha 1 at the bottom to alpha 2 at the top. So again, sort of glossing over those trig games that they're playing, we get to a new integral expression, which is h is equal to negative I over 4 pi rho, so all of that's going to come out because it's a constant in our phi direction, times the integral from alpha 1 to alpha 2 of sine of alpha d alpha. So if we evaluate that, we're going to get our final expression for h, which is I over 4 pi rho, and that's multiplied by cosine of alpha 2 minus cosine of alpha 1, and that's in our phi direction. Now again, it's important to note that our phi and our rho are locally defined. So phi, rho, and our u of phi are all locally defined. So these are not the same things that we talked about in our cylindrical coordinates. They are defined somewhat similarly, but we can't necessarily we don't want to be thinking about these as some distance from the z-axis in particular, rather it's the axis of the current. So, for instance, this rho, remember, was our perpendicular distance. So perpendicular distance from the axis of the current, so from the axis of our line current to our point of observation. And so of course we see that coming in our equation here in this denominator of that final h equation. And then the other thing is that u of phi direction. And so an important note then is that our u of phi direction is given as u of L, which is our differential length direction, cross u of rho, which is going to be the u of rho is the direction of that perpendicular distance. So this is an important piece of information that needs to be included when we use this general h equation here.